Hello and welcome back to Calculus 1 on this glorious Saturday morning. Good morning. Today we are starting chapter 5. We're going to talk about integration. And we are going to see what it means eventually and some interesting facts about it. So we are going to start with approximating area under the curve, which will eventually build into what we know as definite integral through something called Riemann sums. We'll get there. So let's start by looking at the rectangle with sides 4 and 2, where you would say 2 times 4 is 8. Very good. Now, more general case, you would have just say A and B, so area is equal to A times B. Now, we can prove every area formula using integration eventually, and we would like to see what is the connection and how to build that integral which could achieve that. Now, we know how to find area of rectangle and then a circle and then the triangle and then trapezoid, maybe, right? But my question is, what is the area under this random curve f of x between two values a and b? So what would be this shaded region here? And how can we figure it out? So that's what I want to know. What is that area? We can achieve that by slicing the region like this, and then we can use the left-hand points to create rectangles. So now, as you can see, we created a sequence of numbers from x0 to x4. I'll call those left-hand points. Because each out of 5 rectangles that I have here has one of these points as a top left point. So I'm calling them left-hand points. So they're top left points. And it is from that point that I drew horizontal line to complete the rectangle, because the top of the function is curvy, right? Top of the function is curvy, so it's not going to be a rectangle when I chop it up into smaller regions. So to create the rectangle, I already have horizontal line on the bottom. I just want to create horizontal line on top. Now, if you take one of these rectangles, it doesn't matter really which one, we're just going to draw this larger. So let's say this is a rectangle number 4. You will see that rectangle number 4 stretches from x3 to x4, and the point on top, which defines the height, is given as x3 comma f of x3. So we are computing the function at x3 value. So if I am able to figure out what are the values for x0, x1, x2, and so on, I will be able, because I do have a function given, I will be able to figure out how much is f of x0, f of x1, f of x. So I will be able to figure out all y values by simply plugging those numbers in. So now you can also see that the area of these rectangles, so the area that rectangles will cover, is very close to the area that the that is under the curve. It's not the same, but it's very close. So now when you are looking at this, you say, well, the true area is approximated by the area given by rectangles. Sorry, sum of all areas. So I'm going to use this symbol for summation. So in this case, this symbol, we're going to see much more of this symbol. This is summation, sum, addition. So now you have this. Let's see what we can do with this. I can say that the area of each rectangle, I'll just call it AR, is equal to, oh, I did not define one. I need to define one more thing, and I'll define that in delta x is xn minus 1. So an example, x3 minus x2, okay? So it's the difference of two consecutive points. Area, the length in between could be any value, could be 1 unit, could be 3 units, could be half a unit, whatever it is. So now, if you look at the picture, you have the width right on the bottom to be delta x, and you have the height to be f of x3 in this case for this particular rectangle. So now, when we establish that, we can see that the area of the single rectangle piece is going to be delta x times the function computed at the value x0, x1, x2, x3, whatever you need it. Now this delta x that you see here eventually is going to be the dx that I told you that you have to drag around everywhere. It's not there for decoration. I don't know why, but I lost the word sum over here. So now I would like to do the example, and we are going to take a look at the picture for that example. So here is here's the function. What happened?
So welcome to drawing 1 on this glorious Saturday morning.
Drawing 1, yes. So let's say this is a square root function, and I would like to find area between 1 and 4. So you decide to cut at every integer. I mean, we can go from 0 if you want to, but let's do 1. So A to B. So find area under square root of x on interval 1 to 4. So here is what I'm looking for. Now you see that I have, since I used every integer, I have 3 rectangles. Rectangle 1, rectangle 2. Actually, I don't want to label them. Doesn't matter. So I have x0, x1, and x2. I'm going to draw the rectangles in, because I'm using the left-hand point. You can do this with the right-hand point as well. So I draw rectangles, and area L using the left-hand points is going to be, now delta x is clearly 1. I hope you see that, because 2 minus 1 is 1, or 3 minus 1, 3 minus 2 is 1, or 4 minus 3 is 1. So delta x is definitely 1. So AL will be function computed at x0, delta x, that's the first rectangle, plus function computed at x1 times delta x, plus function computed at x2 times delta x. So these are 3 rectangles that you can see on the picture. You see that the height of each rectangle is when you compute the value where you're measuring the height in the function. So now you can see that this is actually f of 1 plus f of 2 plus f of 3, all factored together, times a common delta x, which I can factor out because that's all of them combined. And now you can plug in values, so square root of 1 plus square root of 2 plus square root of 3, everything times 1, which is 1 plus 1.4 plus 1.7. We don't have to be too precise with this, to get 4.1. So area under the curve is about 4.1. Now I can do the same using the right points. If I go to the same picture, and let's say in blue, I pick the right point for each interval, you hopefully see that now you will be overestimating the area. So the first time with the left points, for this particular example, we underestimated, because you see that this part over here is counted in the area, and the one above, this little sliver, is not, right? So the 4.1 that we got is actually less than the true area of the under the curve. But now if I decide to use right-hand points, I will draw rectangles from the right. Every single one of these pieces has a left point and a right point. So you can use either left points across the board or right points across the board to do your calculations. And in this case, left points underestimate the area, the right points will overestimate the area. Now with a different type of a function, right? If you have a decreasing function, they swap. So now, if I am to do AR, it will be f of 2 plus f of 3 plus f of 4, everything times delta x. Because you see that the major points which I am using are at 2, 3, and 4, rather than 1, 2, and 3. So they're shifted by 1 to the right, because now we're using right points. So that would be square root of 2 plus square root of 3 plus square root of 4 times 1, which is 1.4 plus 1.7 plus 2, which is 5.1. So now you can conclude that the true area is in between 4.1 and 5.1. This is what we know. Now I can actually compute the true area and tell you exactly where it is. And I will just here put in parentheses that the true area, exact, not true, exact, is 14 over 3, which is equal to 4 and 2/3, which is 4.6666 going forever. So you see that this method worked, right? So even if you average these two and land into 4, 6, it's pretty good.
Wait, how did we get 14 over 6?
We are supposed to learn that soon.
Ah, okay.
I was just verifying that the answer was okay, right? We got 4.1, we got 5.1, and then I used the magic. Yes, I used the magic. I used the force to find that 14 over 3. But then you say, oh wow, that's a whole point off. Can we do better? And the answer is yes, we can. How do we do better? We do better if we increase the resolution, if we put in more rectangles. If I take each rectangle that exists and cut it in half, like this, if I do that, observe what happens on the top. This portion that I'm coloring right now used to be counted as error because it wasn't within the big 1 to 2 rectangle. But now that I have 1.5 in between, that little black rectangle on top is now part of the overall area. So as I put in more rectangles, more of these little black, which you can see on each one of these, there's one over here and there will be one over there. All of those will become the part of the, not of error, but of the area. So by increasing resolution, you get closer to the exact area. Now I'm going to draw a new picture. With more of this stuff present. So here we go, drawing 101. So this is 1, it's 2, it's 3, this is 4. And then I'll draw in between at 1.5, 2.5, and 3.5 on the x-axis. Function is still square root of x. It's the y-axis. So nothing changed. I doubled the amount of rectangles, and now when I draw this horizontal left hand, this portion on top, which I'm going to color red, which is error, is now smaller than the error we had earlier. So there is less error now because of increased number of rectangles. So now that I have, now can I do better than this? Yes. Put more rectangles in. Now what happens if you put infinite number of rectangles? Each rectangle will be infinitely thin. And each rectangle will fall under a single point under the curve, leaving no room for red error to form. Which means that if you have infinitely many rectangles fill the space underneath the curve, and there's no room for error, those rectangles will give you the exact area. And that is where Riemann sum kicks in. So when you add those infinitely many rectangles, you get the area. But now let's build that and see how the whole thing works. So now with these new numbers, I have my x0, x1, x2, x3, x4, x5, x6. We have to get used to the notation xn, which at the same time represents all of these points. And then depending on which value you pick, you will have one of these points to compute. So xn, think of it as location on x-axis. Which point are you talking about, right? x3 is 2.5 in this case. So now think about delta x. Delta x is each one of these widths of the rectangle. So formula for delta x will always be b minus a divided by the number of rectangles. B minus a is the so AB, that's the interval. In our case, x0 and x6 are a and b, 1 to 4. So we're still working on the same example. So if you think about it, right, a to b, when you subtract them, you will get this, and then you divide by how many rectangles you have, and you will get one of these lengths. So now you have the formula to compute the width of each rectangle. You know how to compute height. You plug in each one of these xn's into the function to compute the height. So now, what is the formula? So area for the left-hand side, in this case, would be, we know it's going to be times delta x each one. So we are going to write f of x0 plus f of x1 plus f of x2 plus f of x3 plus f of x4 plus f of x5, all of that times delta x. Okay. Well, experiment now, but syncing is back. Still eating the stuff. Now, is there a simpler way to write this? Because you don't really want to write this every single time. And there is. I can say the area from the left will be the summation of all of these f of xn times delta x, where this n starts at 0 and ends at 5. So now this is what is known as summation notation, and we need to work a little bit on it to understand. But this is the formula, the shorthand notation to write the long line above. So let's understand how the summation works. So sums. I can say 1 plus 2 plus 3 plus 4 plus 5 plus 6 is actually summation of n, where n goes from 1 to 6. It is a notation. So you're learning the way to write something shorter. This is us defining something so we can be efficiently lazy. That's all it is. So we are not defining new mathematics. It's just you know, you don't really want to spell your name, you just have some kind of signature, right? So you go there and just say, yeah. And this means you, right? Because you didn't really want to spell, because your name has over 18 letters when you combine. So now you can have any kind of formula, and then this is your counter that will start at this number and end with the top number, and you will have to add every term. So if I am to come up with whatever, say n squared minus 2, that starts, n starts at, I don't know, 3 to 6, I will expand this as the first number is 3. So 3 squared minus 2 plus 4 squared minus 2 plus 5 squared minus 2 plus 6 squared minus 2. So you can have a formula. It's important to understand that this n will use these numbers as counter. You start at 3, so here's your 3, 4, 5, and you end with 6 because that is the top number where it ends. It is just a notation for us to condense writing. You clearly don't want to write out summation of n squared. N starts at 1 and goes to infinity, because you can't, right? You can just go and say, oh yeah, it's 1 plus 4 plus 9 plus 16 plus 25 plus 36 plus 49 plus, and then you get bored. So these sums allow us to put these organized addition, right, which can be organized through the set of natural numbers in some way, whether it goes to a finite value or to infinity. It allows us to condense that writing so we don't have to write a million terms. So now, if you go back to our example, when you hopefully understand sums, you see that I will be using the square root of 1, square root of 2, square root of 3, square root of 4, square root of 5, square root of 6, right? Square root of 7. So I can apply, and then times delta x, right? It's summation. So you will multiply each term by that delta x, because you have to understand that, you know, even this new evil symbol, right? It looks fancy. That's addition. Multiplication is still stronger as the, right, with PEMDAS, using the PEMDAS. So it's a higher order operation. So you will have to compute one, then times delta x, then plus another one times delta x, and so on. Or technically understand that, right, this is that, and then you have times delta x at the end. Now I hope that you already are seeing here from this part, f of x dx, and you hopefully are starting to put the picture together today. And what is the first letter for this thing? What's the name for this thing that I circled? Summation, sigma. What's the first letter in that one?
S.
Yeah, S. There you go, right? So we'll get there, but that's actually what it is.
Oh.
Uh-huh. On my planet, that means hope, okay? It's not an S, it's hope. There we go. I know. Some of you will understand, some of you will be staring at the screen saying, what the hell is going on? All right. That's just where I come from. Don't worry about it. Okay? So now going back to my problem. I am going to start we'll draw, a few of these today. So I'm going to start my partitioning between 1 and 4, and then I'm going to add extras in, and then I'm going to add extras in, and I'm going to add extra, and I'm going to add extra, and I'm going to add extra, and I'm going to add more, and I'm going to add even more, and I'm going to add even more. So now, what is happening here? I can't escape the fact that I am on the interval, closed interval, which includes endpoints 1 and 4. I cannot escape that. So my delta x must remain b minus a over n. But b minus a is always a constant number which you are now dividing by infinity. So how thin is each rectangle? We say infinitely thin. It's not 0. It is approaching 0. And this is where a lot of people kind of fall off the bus now, because you're just multiplying by 0. What the hell, right? Well, eventually, right, we'll learn that infinity times 0 is not necessarily 0. We had that in L'Hopital rule, right? Did we? We did. So, what am I going to do now? I am going to, and now, guys, the best thing to do right now is to just stare at the screen to see this. Look at this. I am going to take my points, which are the heights, and multiply that by a width to come up with a single rectangle. Then I am going to add all of the rectangles that I have, and then I am going to send that number of rectangles to infinity to make sure that the error is gone. So I'm going to write this one more time from scratch so that we can see the logic of building the formula. I am going to take all of the heights, multiply them with the width to create the area of the rectangle. Then I am going to add all of the rectangles that I have together, and then I am going to send the number of rectangles to infinity to partition it like crazy. So now what you got here is what we call the Riemann sum, which in short is written as the integral from a to b of f of x dx. Dx is the same as delta x. They share the common value, so they're identical, and you know that from differential section in chapter 4, where we said that the delta x and dx are the same, and delta y and dy are not the same, but they're close. You learned that chapter 4. It's due for your next exam, right? So now you have this dx equals delta x equivalency, and you know the formula for delta x, right? We had it earlier, boxed in red. So this formula is called the Riemann integral, and we can use it to find area under the curve. So, as I said, when you have a rectangle, triangle, or stuff from geometry that you know how to deal with, you already know the formulas. You memorized them 10 years ago, 15 years ago. But what is the formula for area under the curve for square root of x, sine x, tangent x, ln x squared plus 1? You know what I mean? You can have any kind of a curve, and you will need to be able to find those areas as well. So this is the formula that computes. Now, you were interested earlier how I got 14 over 3. Well, I did the integral of square root of x dx from 1 to 4, because the interval a to b is 1 to 4. Now this is integral of x to 1/2 dx, and we know that the integral of 1/2 is x to the 1/2 plus 1 divided by the 1/2 plus 1. And now we don't put plus c, we put this vertical bar because we have to compute. So this is new now. And I will write the formula when I'm done. So that's going to be x to the 3/2 divided by 3, and I'll put halves up to fix the double fraction immediately. And the formula is you plug in the upper value first, and then you plug in the lower value, you subtract. So the lower value next, and then you compute. So square root of 4 is 2, 2 cubed is 8, so you have 2/3 times 8 minus 2/3 times 1. And those of you who like to compute the way I like, 8 minus 1 is 7, so clearly 14/3. Or you can do whatever else you do. So there it is, it's 14/3. Now here I also presented for the first time the most important formula of integration because it's application of it, which says that the integral a to b of f of x dx is any antiderivative f of a from your previous section, f of x, computed from a to b, which is f of b minus f of a. You are going to use this on a daily basis. You are going to use this in physics. You are going to use this in engineering. This will never cease to exist as long as you're taking science classes. I don't care which course. All of them must have it. Definite integral. Now this is already 5.3, but I'll go back to 5.3. So integral of f of x dx is equal to any antiderivative, which is compute the upper limit and then subtract the lower limit. That's how you compute it. All right, now back to 5.1. In 5.1, we are going to now use the rectangles to painfully approximate the area under the integral, under the curve. And then we build it up to this idea and finally realize that we can just do the integral to find the area under the curve. Now there are things that you have to learn about when the function goes under the x-axis and so on. There are things to learn. So, and that's all in 5.2 and 5.3 coming up. So what we're going to do for 5.1, well, I'm going to challenge you now to use left and right sums. So use left and right sums to approximate the area under the curve from, say, 3 to 7 for f of x equals to x squared minus 2. Well, so draw the graph. Just draw the wide parabola, right? And then how many convenient rectangles can you draw? 4, right? From 3 to 4, 4 to 5, 5 to 6, 6 to 7, so that's 4 convenient rectangles. And then compute their left and their right sums.
with some values on it.
Delta x index is 4, right? So it's just 173. Yeah.
I'm a little bit freaked out because the temperature in the classroom is good.
What?
I'm a little bit freaked out because the temperature in the classroom is really too cold, too hot.
I hate, yeah, I hate that air conditioning.
Well, you have to. You need to like go by
Or no?
any AC or something. Oh no, we are approximating 5-1. That's why I just wanted to tie everything in to see how this builds and why do we do this approximation. And then after this example, I'm going to, well, now I'm telling you, there are functions that cannot be integrated. So this formula cannot be used. You have to do this. And you program a computer to break it into 10,000, 100,000 rectangles to get a pretty
Why?
damn
Because you can't
approximation.
use infinite interval?
No, because the integration doesn't work. There are functions that you can integrate. You can differentiate anything and everything. You can differentiate.
Mm-hmm.
But you can't integrate.
That's right.
Yeah.
Is that more after? Yes.
It's just a form of the function.
I was using like the sum.
Whatever, just do it.
Whatever. I guess it's up to you.
Right.
You know, it's
Which one? That will be one. Well, no.
that would be 4, right?
The number times the number of then
So in this case, it would be 1 when you divide by
That's fine, there will be inverse for every function, but there is no inverse function.
Yeah. No, you're right. I just it's weird.
Or
like that is or something else you can do that.
it's just that there is no function whose derivative will produce that answer. That's the point. There's no time.
Oh, so it's all good to do anything.
Explain it.
As well? You're following me.
Drop a plastic cup, bend over and pick it up, right? You drop the glass, right? And it shatters. Right?
It's like
So,
cats with a better
the
cut.
situation is like there was
You just release them out into the wild and they're fine.
because you picked it up. Where there's no undoing situation for breaking the shattering the glass. It's the same situation here. Some functions can be integrated because
Don't know what I'm gonna do in my
they
life now.
differentiate into integrated. Some can't be integrated at all because there's no derivative against them. It's a little tricky. So it's 5-1, which is just 5-1 is like middle school work. You're
Yes.
just multiplying. There's nothing hard. This is technically the only example we look at, and then we move to the scary stuff.
I know you guys get them.
So to solve this, I'm going to draw any. That's a terrible drawing. So here's a parabola, which is even worse. And it goes through -2. And I'm going to say, okay, 3, 4, 5, 6, and let's say 7, whatever. Using the left points, it's going to create rectangles. And I see immediately that delta x is equal to 1. You don't have to do anything fancy, right? You see delta x is 1 because you decided to have 4 rectangles because it was convenient. Go ahead, use 5 rectangles if you like pain, because your delta x will be a fraction. It's not impossible, right? It will just be 7 minus 3 is 4, so 4/5 for each delta x. You can come up with any number of rectangles. It doesn't really matter because it will always be 7 minus 3 is 4 divided by whatever value, whatever number of rectangles you choose. So you can pick anything, really. Now, clearly, the more rectangles you pick, more calculations you have to do. So now what do I have? For the left areas, all I need to do is to say f at 3 plus f at 4 plus f at 5 plus f at 6, and we stop, times delta x. Because we stop at 6 because 6 is the start of the last rectangle. 7 would make another rectangle, so 7 is the left point. Remember, you are looking for the left point, so don't use all of the points. It's either the front one or the last one that it's used, never both for these guys. So we use 3 because it was a left point, and a 7 is the right point, so you will use it later. You will not use 3. So what do I have? I have 3 squared minus 2 plus 4 squared minus 2 plus 5 squared minus 2 plus 6 squared minus 2. All of that times 1. So that's 9 minus 2 is 7, plus 16 minus 2 is 14, plus 25 minus 2 is 23, plus 36 minus 2 is 34. And now you add all of these, so we have 30, 60, 78. Do we all have 78? Now you do the right points, which is you are not using f of 3, you are using f of 7. So area from the right is f of 4 plus f of 5 plus f of 6 plus f of 7. All of that times the same delta x, which is 1. So what do I have? 4 squared minus 2 plus 5 squared minus 2 plus 6 squared minus 2 plus 7 squared minus 2. All of that times 1. 14 plus 23 plus 34 plus 47. So 4, that's 111, 18. Right, 118? Yep. You have 70, 100, 111, 118. So the true area is in between 78 and 118. Now, I already told you how to get the exact one. I was not supposed to all the way through, end of the 5-2 and then use it in 5-3. But, what the hell? Here we go. So we go 3 to 7 of x squared minus 2 dx. I hope that you see why you cannot ignore dx. Dx is delta x, which gives you the width for computing areas. It's not there for decoration. Guys, mathematicians are probably the laziest people in the galaxy, okay? Which is the reason why we constantly generalize things so we can write less. If this dx was there just for decoration, it would be thrown away. It's not. It's times dx. So we get our x cubed over 3 minus 2x computed from 3 to 7. And you plug these values. So it's 1/3 7 cubed minus 2 times 7 minus 1/3 3 cubed minus 2 times 3. And you compute this. So 49 times 7 is the same as 50 times 7, which is 350, minus is 343. Minus 2 times 7 is 14. Minus one of the 3 dies, so 9 minus 6. Now, to subtract 343 minus 14, oh yeah, I forgot to divide by 3. Oh, thank you. Common denominator. Wow. So 3 plus 4 is 7, plus 3 is 10, not divisible by 3. Yeah, so we're going to go 14 times 3, right, which is 42 over 3. All of that minus 3. I don't need these parentheses. So 43 minus 42, so that's 301 divided by 3 minus 9 over 3 to find the common denominator. And the exact answer is 292 over 3. Again, not divisible, right? Because sum of digits is 13. So 29 divided by 3. So now you can actually figure that value out, right? It's 9, 7, and 1/3, right? So 97 and 1/3. It's somewhat in the middle, right, of the two. So if you are to average this, what would you get? What's the half of this? That's plus 20, so 98. The half is 98, and this is 97 1/3. So, I mean, averaging will get you close, but it will not. It's not supposed to get you at the exact area. Good. So that is approximating areas under the curve. We understand how is this done. We understand the left point, the right point, and now it's time to move to 5.2 to see and define definite integrals, to see the Riemann sum at work, and then become concerned for a little while, and then we'll clear it up. All right, so I'm going to restart the stream for the by stream.